Welcome back, everyone. We're diving into some seriously mind-bending physics today.
Yeah.
Non-locality in quantum mechanics.
Yeah, this is going to be fun.
You guys sent in some awesome material on this, especially this essay by Jörg Schneeppert. It's called, and I hope I'm pronouncing this right, Nichtlokalität, Quantenverbindungen jenseits der Distanz.
You got it.
So we're going to try and break this down together, right?
Okay.
What exactly is this spooky action at a distance stuff, and why should we care? What do you think?
Well, basically it means that two particles, no matter how far apart they are, can be linked. And they can influence each other, like, instantly.
Whoa, okay. That already sounds pretty wild. Like, defying the laws of physics as we know them. Wild.
It does kind of defy our everyday understanding of cause and effect, yeah. Even Einstein had trouble wrapping his head around it.
So is this like just a theoretical idea, or is this spooky action actually happening?
How it happens. To understand how we know that, we got to go back a bit. Back to the 1930s, there was this thought experiment called the Einstein-Podolsky-Rosen paradox.
The EPR paradox. I've heard of that. It's like Einstein and his buddies saying, hold on, this quantum stuff, it's just too weird to be true. There's got to be a simpler explanation. Did you ever feel that way when you were first learning about this? Like, it just couldn't be real.
Oh, absolutely. It's natural to question something that seems to completely go against everything you thought you knew about the world.
Right. It's like, wait, what? So what did they think was going on then, if not this spooky action?
Well, they proposed that there had to be something else, some hidden variables, like some property of these particles we just couldn't measure yet, and that would explain this apparent action at a distance without needing anything too crazy.
So they were looking for something more logical, something that fit with our everyday experience, which makes sense, right?
Exactly. But here's where it gets really interesting. Decades later, in the 1960s, a physicist named John Bell came up with this theorem. And this theorem actually gave us a way to test whether Einstein's hidden variables idea was right, or if quantum mechanics was actually describing reality as it is, spooky action and all.
Okay, so we went from a thought experiment to an actual testable theory. That's huge.
Huge. Bell's theorem totally changed the game. It led to experiments that could actually differentiate between the predictions of, like normal classical physics and those of quantum mechanics.
And what did those experiments show? Like, which one was right?
Well, in the 1980s, a physicist named Elaine Aspect did these groundbreaking experiments, and they provided really strong evidence in favor of quantum mechanics and non-locality. Like, he basically showed that Einstein's doubts were unfounded.
Whoa, okay. So, like, these experiments actually proved that this spooky action at a distance is a real thing.
Wow. What does Schneeppert say about those experiments?
Well, Schneeppert talks about how crucial they were. They basically confirmed non-locality. And he also points out the connection between non-locality and another crazy concept, quantum entanglement.
Okay, wait. Entanglement? That sounds kind of sci-fi, to be honest. What does that even mean? Yeah, it's a bit of a mind bender. So entanglement is when two particles are linked, but in a way that even when they're separated, their properties are correlated. It's like they share a single destiny, even across huge distances.
Okay, I think I need an example. My brain is starting to hurt a little bit.
All right, imagine two coins. But these aren't normal coins. Instead of just heads or tails, they can be both at the same time, like this blurry in-between state. That's called superposition.
Okay, I'm following so far. Superposition, two sides at once.
Right. Now imagine those coins are entangled. So if you measure one coin and it collapses into heads, the other one, no matter how far away it is, instantly collapses into tails. Every single time.
So it's like they're connected by this invisible thread or something, and by looking at one, you're instantly affecting the other. That's pretty wild.
It is.
So this whole entanglement thing, does it only happen with, like, hypothetical coins? Or does it happen in the real world?
It happens with actual particles, like electrons, photons, the real deal.
And that's where things get really exciting.
Exactly.
Because this seemingly bizarre phenomenon, it's actually the basis for some pretty incredible technologies. Schneeppert mentions a few of those in his essay.
He does.
Okay, so let's talk real-world applications. Are you telling me this spooky action isn't just some cool science fact? It actually has uses, like out there in the world.
Oh, yeah. And one of the most promising areas is quantum cryptography. Schneeppert really digs into this in his essay.
Oh, wow. Okay, so we're talking about, like, unhackable communication.
Yeah.
That sounds like something straight out of a spy movie.
It does, right. But it's becoming a reality. Quantum cryptography uses non-locality and entanglement to make communication systems that are practically unbreakable.
Unbreakable?
Yeah.
So how does that even work? Is it like entanglement creates some kind of secret code that only the sender and receiver can understand?
It's even more interesting than that. Remember how we talked about measuring one entangled particle?
Yeah.
How it instantly affects the other one? Well, in quantum cryptography, if anyone tries to intercept the communication, to eavesdrop, they'd inevitably mess with those entangled particles. And that would alert both the sender and the receiver that someone's listening in.
Hold on. So you're saying if someone tries to hack into a quantum communication channel, just by listening in, it sets off an alarm?
Exactly.
That's insane.
Yeah, and Schneppat even gives a specific example, the BB84 protocol. It uses the properties of entangled photons to make sure that any interception would be immediately detected.
So in theory, you could have completely tamper-proof communication.
In theory, yeah.
Wow. So think about, will this affect you? Imagine a world where your online banking, your medical records, even top secret government communications, all truly secure thanks to quantum cryptography. It would be a complete game changer for security and privacy.
Absolutely. And that's just one application. Schneppat also talks about how non-locality is being used in quantum computing, which has the potential to revolutionize so many fields, medicine, material science, you name it.
Okay, quantum computing. Another one of those buzzwords we hear all the time. But I'll be honest, I'm still not totally clear on what it is or how it works. How does this mind-bending concept of non-locality actually get used to build a super-powered computer? Like, what's the connection?
It all comes back to those entangled particles. Quantum computers use things called qubits. They're like the quantum version of bits in a normal computer. But here's the key difference. A qubit can exist in a superposition of states, meaning it can be 0 and 1 at the same time.
Wait, how is that even possible? It's like a light switch being both on and off simultaneously.
That's the magic of quantum mechanics, I guess you could say. And this ability to be in multiple states at once is what gives quantum computers their incredible power.
Okay, I'm trying to keep up. We've got these qubits, they can be in multiple states at the same time. But how does that actually translate into solving problems? Like, what do they do?
Well, when you entangle multiple qubits together, they can actually perform computations in parallel. So they're exploring all these possible solutions at the same time, and that lets them tackle problems that would take classical computers millions of years to solve.
So it's like having a massive team of superpowered calculators all working on the same problem at once, each one exploring a different possible solution.
That's a good way to think about it.
Yeah, I can see why this is so exciting for fields like drug discovery, material science, artificial intelligence. Like, the possibilities seem endless.
Exactly. Imagine personalized drug design, or being able to create entirely new materials, all within our lifetime, because of this research.
That's mind-blowing. But I'm guessing it's not easy to build a quantum computer.
You're right. There are some huge challenges. One of the biggest is maintaining the entanglement of the qubits. It's super fragile, easily disrupted by even the slightest environmental noise.
So it's like trying to build a house of cards in a hurricane.
Pretty much. But even with all the challenges, scientists are making incredible progress. Because the potential rewards are so great. Research in this field is just exploding.
It's really incredible to think that all of this comes from the seemingly bizarre concepts of non-locality. It makes you wonder what other mind-blowing possibilities we might be missing just because they don't fit with our current understanding of how the universe works.
It really does. And Schneppat doesn't just focus on the practical applications. He also delves into the philosophical implications of non-locality, which are just as mind-blowing.
Yeah. I mean, this whole conversation is seriously challenging some assumptions about how the universe works. So, what are the philosophers saying about all this spooky action at a distance? Like, what does it mean for our understanding of reality?
Well, for one thing, it challenges our understanding of space and time. Like, if two particles can influence each other instantly across huge distances, what does that even mean for our notions of separation and locality?
Right. So are they saying that everything in the universe is somehow connected on a deeper level, regardless of distance? That's a pretty profound idea.
It is, and some interpretations of quantum mechanics, like the Copenhagen interpretation, actually embrace this idea of interconnectedness, like it's just a fundamental part of reality. They suggest that the act of observation or measurement can have instantaneous effects on entangled particles, no matter how far apart they are.
Okay, now we're getting into some deep philosophical waters. It makes you wonder if our consciousness is somehow playing a role in shaping reality.
Yeah, it definitely challenges our classical intuitions about a world that exists independently of our observations. But I think the important thing to remember is that these philosophical implications are grounded in real scientific evidence. Because of those experiments that confirmed non-locality, this isn't just theoretical.
Exactly. We're not just talking about abstract theories here. This stuff is real. And Schneepat even suggests that non-locality could help us solve one of the biggest mysteries in physics, unifying quantum mechanics and general relativity. Which is a pretty big deal, right?
It's a huge deal. It's one of the holy grails of modern physics. You've got quantum mechanics, which describes the world of atoms and subatomic particles, and general relativity, which describes gravity and the large-scale structure of the universe. And they've been notoriously difficult to reconcile. They seem to operate under totally different rules.
So it's like two different languages trying to describe the same reality, but they're not quite compatible.
Exactly. But non-locality might offer a way to bridge that gap, because it suggests this deeper level of interconnectedness that could connect these two seemingly separate theories.
So is it possible that gravity, which acts over such vast distances, is somehow a manifestation of this quantum entanglement we've been talking about?
It's definitely one of the possibilities physicists are looking into. It's still a mystery, but non-locality provides a tantalizing clue. It suggests we might need to completely rethink our understanding of space, time, and gravity to get to a unified theory of the universe.
That's amazing. Schneepat also mentions that there might even be a deeper theory beyond our current understanding, one that explains non-locality in ways we can't even imagine right now. It's kind of exciting to think that we're just scratching the surface of what we know about the universe.
I agree. And the more we learn about non-locality, the more questions it seems to raise. For example, we don't really understand how it relates to the passage of time. If entanglement allows these instantaneous connections across space, what does that mean for our linear perception of time?
Right. It makes you wonder if time itself is more fluid and interconnected than we realize.
And what about the limits of entanglement? Could there be particles entangled across galaxies or even the entire universe? Those are big questions, and we don't have answers yet, but they're driving scientific inquiry and pushing us to explore the boundaries of our knowledge. I think non-locality is a really powerful reminder that the universe is far more strange and wondrous than we ever thought.
That's a perfect note to end on. This deep dive into non-locality has been pretty mind-expanding. Inspired by the work of Yorgo Schneepat, we've gone from experimental evidence to real-world applications, and now these profound philosophical implications. It's clear that non-locality has completely changed our understanding of quantum mechanics, and it's opened up a world of possibilities that we're just starting to explore.
It really has, and it's all a testament to the power of human curiosity and the endless capacity of the universe to surprise us.
And to our listeners, I definitely encourage you to keep exploring this topic. There are so many resources out there, from books to articles, online lectures, videos. You can really delve deeper into the world of non-locality and quantum mechanics.
And who knows, maybe one of you listening will be the one to unlock the next great mystery of the universe. Just keep those minds open, those imaginations soaring.
Thanks for joining us on this incredible deep dive. We'll be back soon with another fascinating topic to explore.
Yeah, it really does have uses. It's pretty amazing. One of the most promising areas is quantum cryptography. Schneepat really focuses on this.
Okay, so we're talking unhackable communication. Like seriously unhackable. That sounds straight out of a sci-fi movie.
It kind of does, right? But it's not sci-fi anymore. It's becoming reality. Quantum cryptography uses these principles of non-locality and entanglement to create communication systems that are basically unbreakable.
Unbreakable. So how does that even work? Is it like they use entanglement to create some kind of secret code that only the sender and receiver can understand?
It's even cooler than that. Remember when we were talking about how if you measure one entangled particle, it instantly affects the other? Well, with quantum cryptography, if someone tries to listen in on the communication to eavesdrop, they'd inevitably disturb those entangled particles. It's unavoidable. And that would alert both the sender A and D, the receiver, that someone is trying to spy on them.
Hold on. So you're telling me if someone tries to hack into a quantum communication channel just by listening, it basically sets off an alarm?
Exactly.
That's mind-blowing.
It is. Schneepat even gives a specific example in his essay, this thing called the BB84 protocol. It uses these properties of entangled photons and the way they're measured to guarantee that any interception would be noticed right away.
So theoretically, you could have a communication system that's totally tamper-proof.
Theoretically, yeah.
Wow. That's incredible.
Yeah.
And so everyone listening, think about it. Will this affect you? Imagine a world where your online banking, your medical records, even top secret government communications are all completely secure thanks to quantum cryptography. It would completely change the game for security and privacy.
Absolutely. And that's just one application. Schneppe also talks about how non-locality is being harnessed for quantum computing, and that has the potential to revolutionize everything. Medicine, materials science, the list goes on.
Quantum computing, that's another one of those buzzwords we hear everywhere these days. But I'll admit, I'm still a little fuzzy on the specifics.
Yeah.
How does this mind-bending concept of non-locality actually translate into building a superpowered computer? Like, what's the connection?
It all boils down to those entangled particles, remember? Quantum computers use these things called qubits. They're kind of like the quantum version of bits in a normal computer. But here's the key difference. A qubit can exist in a superposition of states, meaning it can be 0 and 1 at the same time. It's wild.
Wait, how is that even possible? It's like a light switch being both on and off at the same time. It doesn't make sense.
I know, right? That's the magic of quantum mechanics, I guess you could say. And it's this ability for qubits to be in multiple states at once that gives quantum computers their incredible power.
Okay, I'm trying to follow. We've got these qubits, they're going to be in multiple states simultaneously, but how does that translate into actually solving problems? Like, what do they do?
So when you entangle multiple qubits together, you get this amazing effect. They can actually perform computations in parallel. So they're essentially exploring many possible solutions all at the same time, and that lets them tackle problems that would take classical computers, like the ones we use every day, millions of years to solve. It's mind-boggling.
So it's kind of like having a massive team of superpowered calculators all working on the same problem simultaneously, each one checking out a different possible solution.
That's a great way to put it.
I can definitely see why this is generating so much excitement, especially in fields like drug discovery, material science, artificial intelligence. It's like the possibilities are endless.
They really are.
Yeah.
Imagine personalized drug design or being able to create entirely new materials all within our lifetime, all because of this research.
That's pretty incredible. But I have a feeling it's not exactly a walk in the park to build a quantum computer.
Right? Oh, you are absolutely right. It is not easy. There are some major hurdles. One of the biggest is figuring out how to keep those qubits entangled. It's incredibly fragile. Like the slightest environmental noise can disrupt it.
So it's kind of like trying to build a house of cards in the middle of a hurricane.
Yeah, that's a pretty good analogy. But the good news is that even with all the difficulties, scientists are making really impressive progress. The potential benefits are so massive that research in this area is booming.
It's amazing to think that all this stems from this seemingly bizarre concept of non-locality. It really makes you wonder what other mind-blowing possibilities might be out there, just waiting to be discovered. Things that maybe seem impossible to us right now because they don't fit into our current understanding of the universe.
Absolutely. And Schneppe doesn't just stop at the practical applications. He also delves into some of the philosophical implications of non-locality, and those are just as mind-blowing, maybe even more so.
Yeah, I mean, this whole conversation is seriously challenging my assumptions about how reality works. So what are the philosophers saying about all this spooky action at a distance? Like, what does it mean for our understanding of reality?
Well, for one thing, it makes us rethink our understanding of space and time. Like, if two particles can influence each other instantly across vast distances, what does that even mean for our concepts of separation and locality? Does distance even matter in the way we think it does? It's a big question. It's a really good question. And some interpretations of quantum mechanics, like the Copenhagen interpretation, say that this interconnectedness, it's not just some weird side effect. It's actually fundamental to reality, like it's built into the fabric of the universe.
So they're saying everything is connected on some level, regardless of how far apart things are. That's a pretty big idea.
It is. And they even suggest that just the act of observing something or measuring it can have these instant effects on entangled particles, no matter how far away they are.
Okay, now we're getting into some seriously deep philosophical territory. It makes you wonder, right? Like, is our consciousness somehow playing a role in shaping reality? That's pretty wild.
It definitely challenges our classical intuitions about the world and the idea that there's this objective reality out there completely separate from us. But it's important to remember that these aren't just abstract theories. These philosophical ideas are rooted in real, solid scientific evidence. Thanks to those experiments that proved non-locality, this is real stuff.
Right. It's not just speculation. This stuff actually happens. And Schneppe even suggests that non-locality might be the key to solving one of the biggest mysteries in physics, unifying quantum mechanics and general relativity. I mean, that's a pretty big deal.
It's a huge deal. It's been one of the biggest goals in physics for decades. You've got quantum mechanics, which describes the world of tiny particles, and you've got general relativity, which describes gravity and the universe on a grand scale. And they've been so hard to put together, they seem to operate by completely different rules.
So it's like two different languages trying to describe the same thing. but they just don't quite translate.
Exactly. And that's where non-locality comes in. It hints at a deeper connection, a deeper level of reality that could tie these two seemingly separate theories together.
So maybe gravity, which acts over these vast distances, is actually a manifestation of this quantum entanglement. It's kind of a mind-blowing thought.
It is, and it's one of the possibilities physicists are exploring. It's still a big mystery, but non-locality gives us a clue. It suggests we might need to totally rethink our understanding of space, time, and gravity if we want to come up with a truly unified theory of the universe.
And Schneepat even hints that there might be a deeper theory, something beyond what we currently understand, one that could explain non-locality in ways we can't even fathom right now. It's pretty exciting to think about all the things we still don't know about the universe.
It is, and the more we learn about non-locality, the more questions it seems to raise. Like, for example, we don't really know how it relates to time. If entanglement allows these instantaneous connections across space, what does that mean for our linear understanding of time?
Right. It makes you wonder if time itself is more fluid, more interconnected than we realize. And what about the limits of entanglement? Could particles be entangled across galaxies, across the entire universe?
Those are big questions. Questions we don't have answers to yet, but those are the kinds of questions that drive scientific exploration, and they really push us to expand the boundaries of what we think is possible. I think non-locality is this amazing reminder that the universe is so much stranger and more wondrous than we ever imagined.
That's a great point, and a perfect place to wrap things up. So we've taken a deep dive today into non-locality, inspired by the work of Jorgo Schneepat. We've gone from the experimental evidence that proves this spooky action at a distance is real, to talking about some of the incredible applications like quantum cryptography and quantum computing. And we even touched on some of the profound philosophical questions it raises about the nature of reality. It's clear that non-locality has revolutionized our understanding of quantum mechanics, and it's opening up a world of possibilities that we're only just starting to explore.
I completely agree. It's a testament to human curiosity and the universe's endless capacity to surprise us.
And to all of you listening out there, I encourage you to keep exploring this topic. Dive into those resources, the books, the articles, the lectures, the videos. There's a whole world out there waiting to be discovered.
And who knows, maybe one of you listening right now will be the one to make that next big breakthrough in our understanding of the universe. So keep those minds open and those imaginations firing.
Thanks for joining us on this incredible deep dive. We'll see you next time for another fascinating exploration of the world around us.